All right, well, welcome everyone to CC Colloquium for February 16th, Wednesday, February 16th, 2022. We have very few announcements today. I think Ramon has something he wants to share with us.
Yeah, just wanted to announce on behalf of the director, we have the next week on Thursday, February 24th is the community conversation at noon, and it will be more on student-focused topics. So we'll hear from Kellen Whipple and Hillary Hartnett, who are our grad and undergraduate associate directors. So just wanted to put that on everyone's calendar.
Great. So I'm off the hook for a COVID update. So that's great news. Thank you.
Okay.
So that I'm happy to turn this over to Professor Ed Garnero to introduce our speaker.
Great. Thanks, Ariel. Well, today's speaker is Professor Mingming Li, who got here in 2017, and Mingming got his bachelor's in geophysics at Yunnan University in China in 2007. And then in 2010, he got a master's actually doing some seismology at the Institute for Geology and Geophysics at the Chinese Academy of Science in Beijing. He came to the States at that point and got his PhD in 2015 here at ASU, so I got to meet Mingming in 2010, I guess 10 years ago, or a little more than that. And after getting his PhD, he went on to Boulder, Colorado, and did a postdoc for a couple of years with Shiji Zhang, one of the premier numerical modelers, turning down a postdoc at Carnegie. And Mingming is, he's talented in many things, like including musical instruments. He plays a number of instruments really well. Chinese stringed instrument, the pipa, which you need to hear him do that because it's really awesome. And he's an expert at numerical modeling or geodynamic modeling. We call him a geodynamicist. And he studies essentially convection in planets. And he works with seismologists, geochemists, petrologists, tectonicists, mineral physicists to decipher the thermal composition, evolution of planetary interiors, Earth and other planets, as well as planets outside our solar system. How do they evolve differently from Earth? And so Mingming's interested in the nature of convection and surface processes that relate to it and vice versa. So today he's going to tell us about unstable structure and dynamics in Earth's deepest interior. So take it away, Mingming.
Thank you. Thanks for the introduction. Let me share my screen. Let me go to presentation mode. Can you see my presentation?
Yes.
Okay, great. So this is my first slide. Okay, so thanks everyone for coming. I hope you all feel very good today. So today, this afternoon, I'm going to, let me make this very small. So today I'm going to show you one of our very latest, very recent work, like in about understanding the deep mantle structure and the dynamics. Okay. So my research focuses mostly on the deep interior of the Earth and other planets as well. This is important and is because the geological events on Earth's surface actually on other planets as well, like plate tectonics, earthquakes, topography, volcanoes. They are all like less or more linked to its interior processes. So we can see the Earth very easily just from space, like we open our eyes, we see the Earth. We can all even fly outside of the Earth to the space. We can see long distance into the universe. However, it is very difficult, almost impossible right now to go inside deeper into the Earth, okay? So, but there's a solution for that. And I would say one of the most important techniques that we use to see through the interior of a planet is by seismic imaging. So the the technique is very similar to do a CT scan. Like if you go to hospital, you do a CT scan, it sends out energy into the object, actually into a human body, and it records the energy as well by recorders. And then by doing that, we get images of the interior. And can we do a CT scan for the Earth? And the question is yes or no. Basically, Earth, of course, is too big to do something like this, but we can borrow, I mean, we can use similar technique to image the interior of the Earth. So right now, for seismology, the source of energy comes from earthquakes. And most of these earthquakes happen naturally, but there are some also human-induced earthquakes. Okay, and to receive the energy, we have seismic stations. So like, for example, in this figure, shows the US array in the United States. It's very, very dense seismic array. So, and after decades, even after long decades of work from seismologists, right now we know the Earth, like many other planets as well, is layered. Okay, it's overall layered, like 99% is layered. So there's no question for that. However, if it is just simply layered, it's kind of boring. And in fact, they are indeed very small perturbations of physical properties in the mantle, or actually in the crust, in the core as well. And these perturbations are very small, like usually a few percent, and very, very small. However, although these perturbations are very small, they play a very important role in controlling the dynamics, controlling the evolution. And without these small perturbations, everything will become like not that interesting, a little bit boring. Okay, so until the planet died, like there's no more perturbation. And like in this slide, I show several images of the seismic tomography model, and at different depths, like from 100 kilometers depth to near the common boundary at 2,800 kilometers depth. I also show two cross sections here. You don't need to like try to remember the details of these figures, but one thing you do need to remember is that usually in seismic images, people use red color to represent low seismic velocity, and then we use blue color to represent high seismic velocity. Okay, so, and the major question we try to answer is what causes these seismic heterogeneities and how do they evolve with time? And to answer this big question, we use geodynamic modeling. Okay, and the philosophy of geodynamic modeling is pretty simple. We assume that the deep physical processes, they are controlled by fundamental physical laws, like F equals ma, conservation of mass, conservation of momentum, conservation of energy. So these conservation laws. And I put three equations here, and these three equations, they are coupled together, and they link the velocity, pressure, temperature, viscosity, and all kinds of physical property together. And these three equations are quite complex, and most of the time we cannot find an analytical solution for this equation. Basically, that means you cannot just bring up a pen and a pencil and try to find the solution of this equation. It's really difficult, almost impossible. And nowadays, because of development of computational techniques, we can use computers to solve these equations. Like in this slide, the image on the left shows a high performance computer cluster, like which we have been using like since 2012, like at the beginning, right after ISTB4 was open. Okay, and this picture was taken like maybe 9 years ago or more, almost 10 years ago. And this is a small cluster here, but like since right before I came here, like 2017, this ASU has a very, very awesome, like very big high performance cluster, and it includes about about 20,000 CPUs. I think they are still increasing the number of CPUs. So we have been, most of our calculations have been performed on this ASU cluster. Is super fast and it's also free to everyone. So if you want to do some calculations and particularly really expensive calculations, you are free to just create an account on the cluster and then you can use a cluster, use a calculation. It's really straightforward. So this is first part of my presentation. So now let's go to my second part. And in my second part, I'm going to provide you an example about my most recent research about unstable structure and dynamics in Earth's deepest mantle. And all of this numerical work that I'm going to present to you have been performed by the CCC student Chen Yuan, and many of you may know Chen. He is going to graduate and going to leave our group maybe this spring. But we also get lots of help, and the project work study have been the benefit a lot from discussions from like CC faculties and students, including Ed Ganino, Dan Xun, and many other students and faculties as well. So thanks very much. So let's start let me start to telling you the story. So the story begins with this global tomography model. So when I say global tomography model, basically is seismic imaging of the deep interior of the mantle. So as I said before, red color represents regions with low seismic velocity, blue color represents high seismic velocity regions. And the most prominent feature we can see from this tomography model are these two large low velocity provinces, and for simplicity, we just call it as LLVPs, okay? And one of the LLVP is beneath the Pacific, and the other is beneath Africa. So, and later I'm going to call the one beneath Pacific as the Pacific LLVP, and the one beneath Africa as the Africa LLVP. And surrounding the two LLVPs are regions with blue color representing high seismic velocity regions. And these regions are usually interpreted as subducted slabs because they are cold, and they also should have a relatively higher seismic velocity. So let's go to the next slide. This slide is just a video, a very nice video and a 3D view of the locations of these two LLVPs, and the one beneath the Pacific and the other beneath the Africa. And this video is made by Ed Ganino. It's really beautiful. So you can watch it until it's done. So let's go to the next slide. And the LLVPs are very robust structures, and the people have using different techniques, using different data, and they show us different types of tomography models. But in all these global tomography models, we can see these two large low velocity provinces, or LLVPs, like one beneath Pacific and one beneath Africa. The details of these structures can be different model by model, but in all models, these two structures are there in all of these tomography models. Okay, there's no question for that. And let's look into some details of the structure of the LLVPs. And this one in this slide, and on the top right, I show a map of the seismic velocity near the core mantle boundary, and I'm focusing on the Pacific LLVP. Okay, and these are 4 cross sections, like vertical cross sections, ranging from the core mantle boundary. Core mantle boundary means the bottom of the core, or the top of the mantle. Sorry, the bottom of the mantle or the top of the core, the core mantle boundary. Okay, and as we can see, the LLVP, they rise from the core mantle boundary to quite some distance up into the mantle, sometimes reaching the upper mantle as well, and most of them are in the low mantle. And one of the most interesting questions we try to answer is how far the LLVPs can reach, or in other ways, what is the maximum height can LLVP reach? Okay, so there are many ways to answer this question. So most intuitively, you just look at the 2D images cross sections and measure the height. Okay, but because seismic tomographies are not are kind of blurry, it's not easy to do that. And also there are so many seismic tomography models. And to make things easy, and we just come up with a very simple solution approach to calculate the maximum height of LLVPs. So like, for example, in this figure, I show just a cartoon is perfect LLVP. Like in reality, LLVP will never look like this clean. Okay, and the red color represents the location of LLVP, and the blue color represents the background. Okay, and it's from the common boundary at the bottom to the surface. And on the right figure, the figure on the right, I'm going to show you a diagram. The horizontal axis is a horizontal average velocity, and the vertical axis is distance above from the CMB. So next, I'm going to calculate horizontal average seismic velocity at different depths of this vertical cross section. So like, for example, if I calculate the horizontal average at this depth, then I get a point here, which is little bit low seismic velocity. The reason why this velocity is little bit low, because most of these regions are occupied by this LLVPs, and they have low seismic velocity. And as we go into shallow depths, the seismic velocity, the average seismic velocity increases. And if we go even shallower, the seismic velocity even increases even more. Okay, the horizontal average seismic velocity. And if we go outside of the regions of the LLVP region, and it's kind of reaches the maximum seismic velocity. And then we get, basically right now I'm showing you 4 data points, but in fact, we calculate the horizontal average seismic velocity throughout the entire cross sections at different depths. And if we connect these 4 data points, we get a trend. Okay, and as you can see, it starts with low seismic velocity and then gradually increases, and at some point there is a turning point, and the seismic velocity no longer increases even when the depths go to much shallow depths. And we think we can define this turning point as shown by this white circle as maximum height of the LLVPs. Okay, so basically what I'm trying to show you is that the approach is very simple. We calculate the horizontal average seismic velocity at different depths, and which are shown by this dark gray dashed line, and we pick the turning point of this gray dashed line and define it as maximum height of the LLVPs. Okay, and we apply this simple technique to lots of cross sections covering both LLVPs, and we also apply this technique to all of these seismic tomography models, and we get lots of results. And we just pick the cross section that has the maximum depth of this, has a maximum height of the LLVPs. Okay, so in this slide, I show the result of the horizontal average seismic velocity as function of depth. On the right figure shows the Pacific LLVP cross sections, and the left, on the left figure, the right figure shows the results of the cross section above the African LLVP, and there are lots of curves. So right now you don't need to worry about that, but each curve represents one cross section. And by examining the details of these curves, we pick 4 cross sections that shows the maximum height of either of these 2 LLVPs, and this is showing in this slide. So basically we pick 4 cross sections, and they show the maximum height of either the Pacific LLVP and also the African LLVP. Okay, and here is the result of this horizontally average seismic velocity as function of the height above the CMB. So for example, in cross section A and cross section B above the Pacific LLVP, we can see that there is the turning point happens at about this location. So this is about, if you read the vertical axis, this is about 700 to 800 kilometer steps. However, if you look at the cross sections, the two cross sections, C and D cross section on the Pacific LLVP, the turning point of these curves, they occurs at about here, this location, and this location occurs at a height of about 1,700 kilometer steps above the CMB. So basically, this result shows that the African LLVP is much higher, or reaches a much shallower depth than the Pacific LLVP. And the take-home message here is that the Africa LLVP reaches a height of about 1,700 kilometers above the square boundary, and which is about 1,000 kilometers taller than the Pacific one. This is super interesting. So the questions, there are two questions here. The first question is, what causes the LLVPs? Okay. And the second question is, what causes the vastly different height of the two LLVPs? And next, I'm trying to answer these two questions. Very important question. So for the first question, what causes LLVP? There have been lots of debate before. And one of the most popular hypotheses is that the LLVPs are caused by thermochemical piles. So thermochemical piles means they are, these structures have high temperature, and they also have higher composition than the surrounding mantle. And but if the LLVPs are caused by thermochemical piles, and then if we go to the second question, then it becomes, what causes the height of the thermochemical piles? I show you in this figure, the brown color or the golden color shows the location of these thermochemical piles. They are hot, and they are also really dense, and actually they are dense than the background mantle. And these thermochemical piles, they just pushed by this subduction, as shown by these blue colors, subduct slabs into like isolated structures, and eventually they form the two LLVPs, one beneath Pacific, which is this one, and the other beneath Africa. So this is one of the most popular hypotheses to explain the LLVPs. And there are other hypotheses to explain the LLVPs, and we are going, if have time, I can talk about more details later. But right now, let's assume the LLVPs are caused by thermochemical piles, which is one of the most popular assumptions. So next, I'm going to show you some numeric experiments. And by showing you these numeric experiments, I'm trying to answer the question of what causes the height of or actually what controls the height of the thermochemical piles. And this is one of the standard numerical calculation. And there are two videos here. On the video on the left right now is all white, but the video on the left shows the temperature field. Red is hot and blue is cold. And the video on the right shows compositional field. And as you can see, there are two compositions. The black color represents the background mantle or regular mantle material, and the yellow color represents the thermochemical piles. Okay, so and this is our initial condition, and let's run the video. And let me pause for a little while. So right after initial condition, you can see the thermochemical pipe, they becomes very hot, and the red color represents hot, and the blue color represents cold again. Okay, and the reason why it becomes hot is because the CMB, the core is very hot, and it gets heated by the core. The reason why the surface is cold because the surface is the lithosphere is cold is because surface is cold. Okay, because half space cooling, like keeps cooling by the surface. And let's continue long calculation. So as you can see, like usually these thermochemical piles, they just push along by the subduct slabs, and they eventually develop a almost steady state, and we can measure the height of these thermochemical piles. Okay, and the good thing of numerical experiments is that we can change different parameters and see what the result and what the height, particularly in our work, we try to answer what parameters affect the height of the thermochemical piles most. And in this slide, there are the top three figures show the temperature field, and the bottom three figures show the compositional field. And from left to right, and there are three different models, and these three different models, the size or the volume of the pile material that increases. And what we learned from these three experiment is that the size of the piles, they does not control its height. Like for example, as we introduce more and more pile material to the lowermost mantle, to the model, the height the maximum height does not change, except just the lateral extent becomes wider and wider. Okay. However, under these three models, we increase the background viscosity. So as we can see from left to right, the viscosity increases from left to right, okay? And as we increase the background viscosity, the height of the thermochemical piles, they also increases. So basically what we learned from here is that, which is here, piles are taller when the background mantle viscosity is higher, so background mantle is more viscous. And we also learned that the density of the pile material is most important in controlling the height of the pile. For example, here's another three calculation. From left to right, we gradually increase the intrinsic density of the thermochemical piles. And as we increase the density, as you can see, the pile becomes the height becomes lower and lower when it becomes denser and denser. So the take-home message is piles with larger intrinsic density, usually they have much lower height. Okay. And in this slide, I show four figures and about what controls the height of thermochemical piles. In figure A, the horizontal axis, the volume percentage of the pipe, the vertical axis is height. As we can see, the volume of the thermochemical piles, they do not affect the height of the pile. And in figure B is the Boyle's number. The Boyle's number represents the density of the thermochemical pile. Okay, so the higher the Boyle's number, the denser the thermochemical pile. As we can see, the denser the thermochemical pile, the lower the height. And in figure C, the horizontal axis is the background mantle viscosity. As we can see, the higher the background mantle viscosity, the higher the height of the thermochemical pile. And we also design experiments by changing the viscosity of the thermochemical pile themselves. And we also found that this parameter, they do not affect the height that much. And you may criticize that these models are just really simple, just 1D box. It's nothing like the real Earth, which is 3D spherical. However, we did perform models more complex geometry, and we make the box longer, and we also perform 3D models with spherical geometry, and these results are consistent with the results when we perform under 2D Cartesian models. Okay, so that basically that means we get similar results when using more complex and more realist model geometry. And because of that, we usually think as long as the model answers the question, the simple the model, the better. This is our philosophy. And this figure is one of the most important figure in this work. So in this figure, the horizontal axis is the background mantle viscosity. The vertical axis is the buoyancy number, which are showing on the left vertical bar, or the buoyancy number can also be translated to the percentage of density anomaly. So the higher the buoyancy number, the higher the density anomaly. And each box here represents one calculation. So using according background mantle viscosity and buoyancy number or density of the thermochemical pile. Okay, and these pink colors, these pink stars, they okay, and the color of these boxes represent the height of the thermochemical pipe, and these pink stars, they represent the height in the range of the Pacific that is similar to the Pacific LLVP height, and the blue triangle represents the location, the height that is similar to the height of the African LLVP, and these gray crosses represents calculations when the height is very high, but very unstable, almost disappear very quickly. And what we learn from here is that I put a note here. The height of the Pacific LLVP are showing by these pink stars. They can be explained by a wide range of parameters. As you can see, there are a wide range of background mantle viscosity and a wide range of Boyle's number or intrinsic density. And however, to explain the large height of the Pacific LLVP as represented by these blue triangles, it requires the piles to have a relatively lower intrinsic density. And because it's, as you can see, the intrinsic density for the Pacific African LLVP is about like 1.5 to 5%. However, the Pacific LLVP can be more than 2%. Okay, so and we also did some more calculation. We found that if a thermochemical pipe is not dense enough, its height will be greatly affected by the surrounding mantle flow. And next, I'm going to show you another numerical calculation. And in this calculation, the top panel shows the temperature field. Red is hot and blue is cold. And the panel at the bottom shows the compositional field. These dark colors represent the thermochemical pipe, and this light blue color represents the background mantle. Okay, and let's run the movie. It's a really short movie. So this is the end of the movie. As you can see, let's focus on the panel at the bottom. There are 3 thermochemical piles, and one pile which is very tall, which is this one is really high, almost into the up mantle. However, the other 2 piles, they are much shallow. Okay, it's very similar. This pile height is very similar to the Pacific LLVP, and this thermochemical pile height is very similar to the African LLVP. And what we found, let's watch it again. And what we found is that this pie with very large height, it is just being pushed by the surrounding subductive slabs. Okay, and we come up with the reason, and the reason why it is very high is because there are subductive materials pushing from both sides. However, the 2 other piles, they are relatively shallow, much shallower, because there are no cold subductive materials pushing them to very high. So the take-home message is that we found the sinking of subductive slabs, which represented by these cold materials, to the deepest mantle pushes a pile nearby to have large height. So this is very interesting, and we can apply our understanding to help understand the real Earth. Okay, and in this slide, this figure shows the tomography model of the of Earth's mantle, and this is showing near the core mantle boundary depths. And again, we see 2 LLVPs. One is beneath the African LLVP, and the other is beneath the Pacific. We call it Pacific LLVP. And if you still remember, we just demonstrated that the African LLVP is much taller than the Pacific one, although it's 2D figure, but actually the African LLVP reaches a height much shallower than the Pacific one. There's almost like 1,000 kilometers difference between the height of these 2 LLVPs. And one implication from our numerical modeling is that we think the African LLVP may be pushed more strongly by the mantle convection, by the surrounding mantle convection. And as a result, it has much higher height, much larger height, or reaches much higher depth, much shallower depths. But the Pacific LLVP, it may still be pushed along pushed by subduct slab, but maybe not as stronger as that for the African LLVP. Okay, so back to our question, what causes the vastly different height of the two LLVPs? And there are two explanations. The first one, option A, is that the African LLVP is less dense than the Pacific LLVP. And usually less dense materials, they try to rise. Okay, very dense materials, they just don't like to rise, they try to sink. Okay, and the other explanation is both the two LLVPs, they are not very dense. However, the Africa LLVP has been pushed more strongly by convection flow than the Pacific LLVP. So this is very interesting. So if this option A or option B, or if answer B is correct, then the Africa LLVP should have been rising in recent geological times. So by saying recent geological time, I mean like tens of millions of years, actually back to 200 millions of years since the beginning of the subduction, along the Pacific region. Okay, and then the question is, what are the physical properties of these LLVPs? Particularly, what is the density of the LLVPs? And although our numerical calculations suggest the African LLVP may be less dense than the Pacific one, but this is not observation. We really need observational constraints to constrain the density and also seismic velocities of these LLVPs. And also another very big question is, what is the nature of mantle flow? And we hypothesize that the African LLVP may have been pushed by the surrounding mantle flow more strongly than the Pacific one, but we need to test this hypothesis by observational constraints. And another, if we think even more broadly, then another very interesting question is, how does the surface respond to the rising Africa LLVP? Like, for example, how does the rising LLVP affect the plate motion, affects the topography above the African LLVP, affects the gravity, affects volcanism, and maybe affect the earthquakes? Okay, and to answer these questions, we really need a multidisciplinary work, including observational, laboratory, and also theoretical, like numerically as well. So, and we are here together to make it possible. Okay, that's a good thing of CC. And thank you. That is the end of my talk. And if you have any questions, feel free to ask me. Let me check the time. And of course, and since we still have a little bit amount of time, let me come back to the first question: what causes LLVPs? And although in this study we assume the LLVP, they are caused by thermochemical piles, and there are other hypotheses. And some people think that the LLVPs, they are just hot. They are not. They have set the same composition as the surrounding mantle, and they are just hot. And if you make something very hot, and it reduces seismic velocity. However, we think if it is simply hot, if both these two LLVP, they are simply hot, we think it's very difficult to explain. To explain why they can reach much different height. So, and basically our results support that the LLVP, they are caused by these thermochemical piles. And particularly we think the thermochemical piles, they are not very stable and they have been rising. Okay, this is the real end of my presentation. And I'm happy to answer any questions.
All right, thank you very much. We have some questions coming in. Please put questions in the Q&A. Mike Line has one already for you. He says, he asked he says, nice talk. Then he asked, what role do thermochemical piles play in driving plate tectonics in general? And how important might they be on other planets, like especially planets that are many times as massive as Earth?
Oh, that's very good question. So as you can see, the thermochemical piles, they are right above the core, and they are also very hot. And basically, the most important role that it plays is it kind of insulating the heat from the core and make the mantle cool much faster. Okay, and however, the thermochemical piles, they are relatively small. Like the volume is less than 10% of the mantle volume, and they are mostly passively pushed along by subducting materials. And another thing that may contribute to plate motion, to plate tectonic, is that mantle plumes, basically very hot materials, they can rise from above these thermochemical piles. And once these plumes reach the surface, it can cause partial melting and sometimes make the lithosphere very weak, and then sometimes even breaks the lithosphere. And this is one of the lots of people are trying to answer how the mantle plume breaks lithosphere. There are lots of studies on that. But to make everything short, and the thermochemical piles, they affect the thermal evolution, and they also controls the property of the lithosphere, and which may make the plate tectonics happen. And the next one is how important might they be on other planets. And right now we are not very sure whether other planets will have these thermochemical piles or not, because there's no seismic observations right now. But there's no reason to believe that they do not have any thermochemical piles. Like for example, the Mars may have one, the Venus may also have one, and they will greatly affect the thermal evolution, and sometimes may even contribute to make plate tectonics happen, or may sometimes, or it's unclear right now how whether they help plate tectonics or whether they promote plate tectonics. But this is something ongoing research.
Okay, and I didn't quite catch on other planets. Do you think this will be, I mean, this gets to the origin, right?
Yeah, and the answer is we don't know without any observation, but
what would you predict?
Yeah, but we can predict, like the Earth has one, right? Maybe there's nothing special for these thermochemical piles. They just dense, and as long as some planets in the mantle, one part of material is less dense, the other part is more dense, they should have thermochemical piles. Okay, so there's no reason to believe there's no, but without any direct evidence, it's still difficult to say for sure. Okay.
Right. So Steve Ruff asks, he says, the description of thermochemical piles suggests both thermal and chemical differences exist from the surrounding material. So how is this recognized, and what might the chemical difference actually be?
Oh, that's a good question. So the first of all, the temperature is very high, and this is very easy to understand. This is because the thermochemical pile, they just sit above the core, and the core is very hot and get heated all the time, the thermochemical pile. And the reason why it's dense, because it may have different composition, and one of the composition element that is very dense is iron. So usually people think it has more a concentration of iron in the thermochemical piles, which make them very, very dense. And there have been lots of different hypotheses for the origin of the thermochemical piles, like including subducted oceanic crust, and like even starting from magma ocean style. And recently, the student Chen Yuan also proposed that the thermochemical pile may represent some part of the impactor SIA, which impact the Earth before and forms the moon, and still there are some part of the SIA, which we estimate the SIA is much denser than the background mantle, and we hypothesize that the SIA may still in the Earth's lowermost mantle as well, and they form the LLVPs.
Okay, there's a question, I think, from a student. Is there any way that we have technology, or the future technology, to potentially harness geothermal energy from mega plumes? So not quite about piles. It's going in a different direction, but
mega plumes. Yeah, usually when we say mega plumes, like I think about the large igneous provinces. So we do observe lots of large igneous provinces on Earth's surface. They are relatively old, and but we have lots of samples. We can analyze the lava, the rock, which is not lava right now, but the igneous rock from the large igneous provinces. And some of these thermal mantle plumes, because they form from the thermochemical piles. So these plumes may carry some material from the piles to the much shallower depths and then get erupt to the surface. And if so, we can analyze these rocks and tell the composition of the thermochemical piles. That's really good one. Yeah.
Yeah, that's a different question. So Amanda has a very technical question, which I barely understand, but maybe she can explain if needed, if this isn't clear. In your regime diagram, the one of buoyancy number versus mantle viscosity, there's a threshold line defining the location of the pink crosses, the Pacific LLVP. Have you calculated the Rayleigh number for that line or similar trend in terms of relevant non-dimensional number? It seems like there could be an analog in non-mantle plumes. So she's trying to generalize from your mantle plumes to other types of plumes.
Like they could be an analog. Oh yes, the threshold of this line, and on the vertical threshold is basically the background mantle viscosity. So and we tried all kinds of background mantle viscosity, and we can make it even lower, but the trend basically remains the same. And this horizontal threshold, which I mean this one, the minimum points number is less than 0.4, and this is because any number smaller than this 0.4, the thermochemical piles, they just unstable, like exactly the same as shown by these gray crosses. And about what defines that threshold?
Yeah, so I guess she's asking really what defines, this threshold that you're seeing here.
Or the color represents the height of the thermochemical piles. So basically, we just pick the. Right now, we know we measure the Pacific LLVP, which is about 800 kilometers or 700 to 800, and these pink stars represent models with this kind of height of thermochemical piles. I'm not sure whether I fully understand the question. What defines that threshold? The threshold is the height of the thermochemical pile.
Yeah, I think.
I see. So if you look at the thermochemical pile, we just pick the top of the thermochemical pile to define the height. And we, like, when the area of this thermochemical pile falls within 5% of the area as bottom, then we define at the top of the thermochemical pile. Maybe this is Amanda tries to ask. It's very, very technical. That's a very important question. So.
All right, Amanda can chime in if that didn't quite cover it. Here's an interesting, she says thanks. If there are large low velocity provinces, are there small low velocity provinces as well? And if so, what importance do they have?
Oh yeah, that's an excellent question. And actually, we have lots of all kinds of sizes of seismic velocities on the common boundary. At the large low velocity province, they are the largest one. And as you can see, like just from this map, there are lots of small, relatively small blobs outside the large low velocity provinces. Okay, and these results may have relatively low resolution, and they can be even smaller structures and on above the common boundary. And these small structures, and they can even have even lower seismic velocity. And one example is the ultra low velocity zones, and which is much smaller than the LLVPs, but they have much lower seismic velocity. And we think they are caused by partial melting, and they may also caused by different composition. And by studying these smaller structures, we can tell a lot about the thermal and chemical evolution of the mantle, and also whether there is any material exchange between the mantle and the core. It's very interesting topic, and we have been working on this understanding the small structures as well as have been going on for a long time, mostly working with Ed and Danxi in our geophysics group.
Right. Unless there are any other questions, I know Ed has a question he was going to break in here.
Yeah, so you have this big African blob that's moving up, and you don't know necessarily if it's because, you know, you brought up a couple hypotheses, but if you kept your calculation going, does it continue to the surface? Because that would have profound implications for a large igneous province of the sorts Earth may have never seen before, with the volume of heat that will go to the surface.
Yes, that's very good one. So you're asking about the future of the Earth. So if we keep the calculation, if the calculation keeps running, right now I stopped showing here, but if the calculation keeps running, these thermochemical piles, because they are not very dense, they will sometimes just mix with the background mantle very quickly. And some of these materials will reach the right beneath the surface as well. However, because the upper mantle, the mantle convection convects much vigorously in the upper mantle than in the lower mantle. So as a result, it mixes even more quickly in the upper mantle. So, but basically, sometimes it will keep rising as long as it's not dense enough. But if you choose a moderate density, after it reaches very least steps, some of them may just fall back down and then rising again, and it's kind of episodic phenomenon, up and down. And the Pacific one may also up and down if it's not dense enough. But the thing is that seismic observations only show present day image. But if you need to understand the future, we need to do some calculations to give some predictions. Yeah.
All right. If there are no other questions, then we'll wrap up, I guess. Thank you, Mingming. That was a great talk. Really interesting. And just let everybody know that next week will be in person. We have a visitor from out of town, Dr. Chen Zhu from Indiana University. He's actually giving the Darcy Lecture, which is an honorary lecture for Professional Society. And his topic is how are geochemical reactions and aquifers connected to climate change mitigation. So if you are willing to, please make plans to be in Marston Theater. If you feel safe doing so, we'll be broadcasting from there for the rest of you who can't be there. So with that, thanks again, and we'll see you next week.
Everyone. Thanks for your questions, comments.
Okay.